Okay.
So, good morning. Thank you for being here. It's a pleasure to be here after some years. And as Livia already introduced, I will talk about the coevolution between supermassive black hole and host galaxies. Yeah.
Yes, this is just for project.
At high redshift. So there are several open questions regarding the formation of supermassive black hole at high redshift and how they coexist with their host galaxies. In particular, we don't know if they are already co-evolving, but we know that most of the quasars that have been observed are overmassive with respect to their host galaxies, with masses that are at least equal or even like that are at least 1/10 of the host galaxy. We are not sure about how accurate are the measurement of both the black hole masses because they are based on local calibration, and also which are the masses of the host galaxy, because we are limited to far infrared observation to look at them, and there are some tentative measurement of the stellar masses of the host with GWST. And so there's a lot of question, and we don't know if this object that we are seeing, we are looking at a high redshift when the universe was less than 1 billion years old, how they can evolve to if they will reconcile with the local relation between the host galaxy and the supermassive black hole. Indeed, where there are evidence that these objects in particular, when we look at the supermassive black hole that have experienced the highest accretion history, we don't know if these objects are facing a particular evolutionary phase, because what we can see is that they have peculiar X-ray spectra, which are very steep. And the steepness of the X-ray spectrum is connected with the presence of very fast winds, which may be an hint of a coupling of the accretion disk, the wind that comes from the accretion disk, with the coronal emission. Maybe there is a hint for a feedback which is taking place in the inner part, and which may impact the properties of those galaxies on longer time scales. In this context, GWST has provided an incredible amount of results. In particular, has discovered a lot of new AGN of intermediate luminosity, but also allows us to reveal large overdensities close to the brightest quasars at cosmic dawn. And for instance, in this work, a lot of galaxies have been observed, and this confirms that these quasars need to grow in a very dense region where there is a lot of gas, not only in the central part close to the quasar, but also in the surrounding. And this may be some hint that these objects, if they evolve over cosmic time, they maybe benefit from the accretion of gas through merger, which may sustain the growth of those galaxies over the cosmic time, while the supermassive black hole may halt its growth due to the feedback that prevent further accretion onto the supermassive black hole. But also ALMA is very useful for this kind of study, because it allows to reveal the presence of already ongoing mergers, because it allows us to resolve the region really close to the quasar. For instance, for the same target with C+ emission, you can also trace the presence of very close companion galaxies, while with GWST to require an accurate modeling of the PSF, which is not always so easy to do, because these are very bright quasars which have a luminosity above 10 to the 46 per second. And in particular, ALMA also allows us to study the properties of the ISM in those galaxies, and this is the reason for this work, where we focus on the dust and molecular gas properties on all the known quasars at redshift above 7. We we use archival observation and proprietary data obtained with a recent observation at NOIMA. And unfortunately, we only got one detection of the CO, which traced the molecular gas for one galaxy, which had been published by GAEA a couple of years ago. While for the other objects, we only have upper limits on the CO, and for two, we only have a continuum upper limit. And so this suggests that the amount of molecular gas in these galaxies is not so large. And indeed, we compute molecular gas masses for these objects. And we can see that the quasars at redshift above 7, both from our for the entire sample divided by the proprietary data and archival observation, have upper limits which are consistent with the bulk of the population of quasars at the epoch of ionization from the literature, and are consistent also with quasars at lower redshift, in particular quasars from cosmic noon. This suggests that there is no significant evolution, and so they have similar molecular gas masses, which are quite large, of course, because with respect to some local star-forming galaxies, because these are very bright objects, but they are not so rich. And this suggests, as I will show later, that these galaxies have a limited amount of gas in order to build the host galaxy and to sustain the growth of the supermassive black hole. We also have C+ observation for these objects, and we compute the star formation rate from the far-infrared continuum emission, as I will show later. And we can try to see if this measurement of the molecular gas content is consistent with what we can obtain from the C+ emission for these objects. C+ is another tracer of the interstellar medium. It can trace different phases of the ISM, but is already also used to trace the molecular gas in both local objects and high redshift objects. We can see that the C+ emission is consistent with the scaling relation for local objects, the relation between C+ and star formation rate, which suggests that in this object, the C+ emission can at least partially be attributed to the presence of star formation in those galaxies. But as I already told you, we have some problem when we try to use the C+ to trace the molecular gas, because as some simulation suggests, the amount of molecular gas traced by the C+ can also trace different phases. In particular, it appears to be associated with also the atomic emission, mostly to the atomic emission. So this is something that we need to take into account. However, when we plot the C+ emission versus the molecular gas that we derived, we can see that all the quasars at redshift above 6 lies way below the relation from local objects or calibrated at lower redshift. And this means that we cannot rely on the C+ to trace the bulk of the molecular gas with assuming the same physics that is associated to the calibration obtained at lower redshift. However, we can see that these objects have a relation. There is a relation between the C+ and the molecular gas for all these quasars. So we in the paper that was recently accepted, we propose a new calibration with a lot of caveat, the one that I already presented. But this calibration can be used for quasars at high redshift as an alternative to constrain the molecular gas content. And because, as you can see, all quasars lies in this region, which are way below other. And this is also consistent with the result from other publication for objects at the same redshift.
So Francesco, I interrupt you now, but so the molecular gas in the y-axis you executed, can you repeat it again?
This is molecular gas with CO transit, with observed CO transition, assuming an alpha CO, which is consistent for all, is the same for all objects, and is the typical 0.8 alpha CO for luminous galaxies and AGN. And while this is okay. So.
Okay, sorry.
Well, regarding the dust emission, we use the continuum observation to model the far-infrared emission for all these targets, and for these objects we can see that we can measure the size of these objects. These quasars have relatively small sizes, less than 10 kiloparsec, and they are quite compact objects. And we assume a dust temperature because for this object we don't have observation that trace the peak of the far-infrared emission, and we assume this dust temperature based on recent results from the literature that suggest that there is a possible increase of dust temperature at high redshift. Of course, we need to take care of the potential contribution from the quasar, because it is well known that the quasar can directly hit the dust, and there are now several observations that suggest that the contribution from the AGN to the heating of the dust can be quite significant, up to 50% of the total far-infrared luminosity. And so when we measure the star formation rate, we decide to assume that half of the luminosity comes from the direct heating due to the quasar. And with this assumption, we measured the dust masses for our sample, and what we can see here is that we have a copious amount of dust at this redshift. These galaxies have an age which is less than 1 billion years, but they already have masses that are around up to 10 to the 8 solar masses of dust, and this is consistent with the bulk of quasars at this relatively lower redshift, but also with the luminous quasars at cosmic noon, which suggests that all these objects have similar properties, and there is no evolution of the dust masses with redshift. If we further investigate the properties of the gas and dust, we can see that also the gas-to-dust ratio are consistent with what observed at lower redshift, with an average gas-to-dust ratio of 75, which is similar to the one observed in the local universe, which is like around 100. And this means that there is no significant evolution of the properties of the ISM in high redshift quasars. And regarding which are the processes that may lead to the growth of these dust masses, it is still difficult nowadays to constrain the process that may lead to the formation of all these large dust masses. Here I show a region where we expect our quasars to lie based on the stellar masses that have been measured with GWST for 4 of them. Of course, we cannot measure the metallicity in our quasars because the emission is dominated by the quasars, so we don't have a measurement of the metallicity for the host galaxy. And what we can see is that this host galaxy of quasars lies in a region which is consistent with that of rebel galaxies. And in particular, this region can also be, this kind of dust to stellar masses can be obtained with different simulation, assuming both a contribution from growth of the dust particles within the ISM, which may be enhanced in high star-forming galaxies at high redshift, because the ISM condition may favor the formation of dust particles within the ISM, because they have very dense environment. But also the presence of relatively large stellar masses suggests that also the intense star formation and intense stellar process that may occur in the host galaxies of quasars may contribute to the formation of such dust masses within less than 1 billion years. And so, looking at the efficiency at which these objects form, we can see in this star formation rate versus molecular gas mass plot, we can see that the quasars at redshift above 7 are consistent with the luminous quasars at different epoch, both the quasars at cosmic dawn, but also those at cosmic noon. And we also compare with local and lower redshift objects, and we can see that they have relatively short depletion time scales, which means that they will the molecular gas that they have at the moment will only be enough to form galaxies for a very few tens of million years. And so they need to refuel their gas reservoir with mergers or further accretion from the surroundings. We look at the results from the GAEA semi-analytical model to see if these objects can be reproduced with simulation. And what we can see is that if we select the brightest quasars from the SEM, we can see that the bulk of the population of the objects that are being produced with the SEM have lower star formation rate, but they can cover the same regime. And we can also further investigate this by plotting the star formation efficiency, which is the ratio of the star formation rate over the molecular gas mass. And we can see that these objects can be reproduced, but they are hosted in the simulation in galaxies which have lower black hole masses, which means that these bright objects are produced by the simulation with more efficient feedback and more efficient process regarding the quasar, but the host galaxy have similar properties, and so we can already see some of these rare objects in the high universe in our simulation. Of course, we are missing for the moment potentially some of the objects that have been observed with GWST, which are lower luminosity AGN that are hosted in less massive galaxies, and that we need to observe further with ALMA. And what we can see here is if we combine all quasars at different redshift and AGN, what we can see is that if we compare the star formation efficiency versus the infrared luminosity, the quasars, which are all these objects here, combining all the samples from the local universe up to high redshift, we can see that there is a correlation with the molometric luminosity of the AGN. So the most bright quasars are hosted in galaxies which have the highest star formation efficiency, which suggests that the conditions that favor the formation of the brightest quasars are also consistent, also favor the formation of highly star-forming galaxies. And we can see also there that dividing the sample in beam of bolometric luminosity, we reach the highest star formation efficiency in the brightest quasars, which are quasars both at redshift above 6, but also the brightest quasar from the WISH sample, which are the hyperluminous sample at high redshift at the cosmic noon. And there is so a correlation, which means that the condition that trigger the high star formation efficiency in the host also favor the brightest phase of the quasars, and but also we have another option is that the quasar may also contribute to the feedback to enhance the star formation, especially in the central part. What we can know now from simulation is that these objects, which are those from the GAEA here, are objects that after a bright phase of the quasar in this simulation is able to remove most of the gas from the host galaxies, and in this case the quasar then evolve passively, and it never reach such bright phase again in the future, and can only reach luminosity above 10 to the 45 in case of major merger. And so from this, what we can now understand from the simulation is that we expect that these objects may remove most of the gas, or they halt the formation of new stars in the host, and so halting the growth of the host galaxy due to the feedback from the central supermassive black hole. And so in that case, what we need to look are quenched galaxies at lower redshift with massive black hole that are in a luminosity regime which is like 10 to the 44, 10 to the 45, similar to low Battiferro galaxies. And so I leave with my conclusion, where we found that even the brightest quasar, the first brightest quasars, have similar properties in terms of molecular gas and dust to quasars at lower redshift. We can use results from the semi-analytical model to predict the future evolution of these quasars, and we need to further investigate which is the relation between the bright phase of quasars and the properties of those galaxies, because we need to understand which is the one that triggered the other, and so thank you for listening.
Thank you very much. A lot of questions. Carlotta.
Very quick one. How did you derive a H2 mass?
H2 mass?
Just one object as CO detection.
No, we use the upper limits. We use the upper limits to derive upper limits on the H2 masses. And assuming an alpha CO and the CO sled in case of, because some of these objects have observation of intermediate transition of the.
So when you derive the relation with C class, you consider that they are.
Yeah, we also derive this relation using upper limit with the mix.
Roberto?
Very nice work. I'm a little confused by your last statement. You interpret this as an excess of star formation in the most luminous, volumetrically speaking, most luminous region, but could it just be that you are removing the gas? So you have enhanced star formation efficiency just because the numerator is the same, but you divide by a single number.
This may be this is another interpretation about the possibly, let's say, delayed effect of the quasar feedback, where we are seeing that the quasar are still in the bright phase because they need a smaller amount of gas in the central region to sustain the bright emission, while the effect of the feedback over a longer period of time has already removed most of the gas in the galaxy. And of course, this can be another interpretation, but this feedback may be quite efficient in removing all the gas without removing enough in the surrounding of the supermassive black hole. This requires a let's say, nice geometrical distribution of the gas that allows the gas to go to the, of course, but this can also be another interpretation.
Monica?
The question again on the molecular gas and the C2 luminosity relation. Mainly on the alpha CO conversion factor that you use to estimate the molecular gas, because it has been shown locally mainly that the alpha CO conversion factor depends on metallicity, and when you go to the low metallicity regime, then there might be a large fraction of molecular gas that is not traced by CO, the CO dark gas. So I imagine when you go to high redshift, you are again in this low metallicity regime somehow. So I was wondering, one, if you have metallicity in this case, although pink QSOs, I guess, no. And two, if you took this into account somehow as a caveat when you derive this new relation. It might be that the H2 is there, but it's not traced by CO.
Yeah, thank you for the nice question. Well, if you if you want to reconcile this measurement with your relation on the other contained in the local universe, you need to an alpha CO which is like almost an order of magnitude higher. And this, of course, we cannot rule out this option because if we cannot measure the metallicity in this object, and at the moment it's quite difficult because you are not able to disentangle the contribution from the stellar emission and the one from the quasars, because these are very bright objects. Maybe this can be done in relatively lower luminosity GN, but you need to have an alpha CO which is like 10 or something, because
What did you use?
0.8. But if you assume a Milky Way like, you will reach this level, and so you still need. And this is consistent with the result from other work which studied this kind of objects. So this can be an option, but we need very high alpha CO.
Other questions?
I'm very curious about the fact that the vaccine for is greater, stating that can be up to 50%. So if you can go back to that slide. Yes, this one. So the fact is that I think that your sublimation rate comes from the luminosity, and you fit the single modified black body obtain that. But unless you reach a very high frequency, let's say 1000 gigahertz, you should not be able to probe this second contribution from the GN. And so your thing you obtain here would be just the green there, which is not affected by the AGN and should not be affected.
Thank you for your question. Well, as you can see here, you have, of course, you can, what you are saying is quite correct. But in this case, for instance, you have a central temperature which is like, if I'm not wrong, like 70 Kelvin. But there are several objects, also hot dogs hosting obscure quasars, where the temperature is like 100 Kelvin. And so even here, you can, even with this point, you can see that the distribution is more consistent with a higher temperature modified black body, because when you have some point also here, which is some of the objects here in the work by Roberta, they have observation in this part. Also here, not only here, but also here. And also in this case, you can see that you can model them with only a 50 Kelvin, 40 Kelvin contribution. And these are quite compact objects. So the contribution from the quasar in these very compact objects, in very bright quasars, can be significantly extended also in the very central few kiloparsec. And so it's difficult to if you try to model some of them, you cannot model them with a modified black body in 40 Kelvin, because the contribution can also be visible at these frequencies here.
And just is explained by the dust temperature fraction, or really needs particular?
Oh, well, there are this is there are evidence that there is a dust gradient, a dust temperature gradient. So if there is only an effect of the dust temperature evolution, you expect that the gradient is not so steep as in some objects which have spatially resolved observation of the dust temperature.
Okay, let's see if there are questions online. I don't know. No. Okay, if not, let's thank the speaker again.